Assalamualaikum students, welcome to Electronics. I'm Madam Rosmina Zwin Abdurrahim. So as usual, let's start with one hadith. Abu Hurairah reported, the Messenger of Allah sallallahu alaihi wasallam said, whoever calls to guidance will have a reward similar to those who follow him, without detracting from their rewards at all. Whoever calls to misguidance will have sin upon him similar to those who follow him, without detracting from their sins at all. Source Sahih Muslim. Okay, so this hadith would like to emphasize be careful in our actions, okay, because we never know if our actions will be followed by others. Okay, if it is good things, alhamdulillah, we are going to get double rewards, but if it is a bad thing, be careful because our sins also will be doubled. So we are still in chapter 4, bipolar junction transistor. In this video, chapter 4b, there are two subtopics. The first one is on BJT DC Analysis and the second one is on BJT Load Line. Okay, for BJT DC Analysis, we are going to have a look on DC analysis related to BE loop, CE loop, as well as we are going to do some calculations related to node voltage as well as the current. Okay, so let's have a look on this one particular circuit, which is the common emitter circuit. As I mentioned before, common emitter circuit is the most common circuit in BJT amplifier. Okay, for this particular common emitter circuit, as you can see here from this schematic, we have the CBE, okay, the BJT symbol. Obviously, this is NPN type because the arrow is pointing out. So at the base, as you can see here, it is connected to RB, which is later connected to VBB. And at the collector, it is connected to RC, which is later connected to VCC. And as you can see from here, emitter is grounded. Okay, so when you want to do the DC analysis, you can actually use the original circuit here, okay, to calculate for whatever parameters needed, the currents, the voltages. Okay, but actually in DC analysis, we can have one DC equivalent circuit that can be represented by this schematic. Okay, so as you can see here, base and emitter, actually it is represented with one diode, okay, because it's forward bias, remember. Okay, so there will be one diode, so that's why the voltage between base and emitter always will be equal to 0.7. okay, unless given, always assume VBE equal 0.7 volt. Okay, for the same circuit just now, let's have a look on the BE loop. Where is the BE loop? It is the loop involving BE junction. So as you can see here, this is the B, this is the E. So meaning the loop here is actually this loop. Okay, the BE loop, or sometimes we call this as input loop. Okay, so in this particular loop, we can just simply do KVL. Okay, when we do KVL, if we rearrange that KVL equation, we are going to get this equation of IB. Okay, it's coming from the KVL equation from the BE loop. So once we know the value of IB, we can simply calculate the value of IC, because IC is given as beta IB. Then obviously from there we can also calculate for the IE. So basically from the input loop or BE loop, we can calculate all the currents. Now let's have a look on the CE loop, which is also called as output loop. CE loop is the loop involving CE junction. So as you can see here, this is the C and this is the E. So the loop involving CE junction is this loop, right? Okay, so this is called as CE loop, or sometimes it is called as output loop. So what you can calculate from here, you can just do KVL equation. So if you do KVL for this particular circuit, you are going to get VCE equals VCC minus ICRC. VCC always given, RC given, IC you already calculated from BE loop just now, remember, when we calculate the currents. Then simply from here we can calculate for VCE, voltage between collector and emitter. Okay, let's have a look for this particular example. So in this example, we are supposed to calculate for the all three currents, base, collector and emitter currents, right? And we are supposed to calculate for the CE voltage, which is VCE. And for this circuit, all the parameters, circuit parameters are given: VBB, RB, RC, VCC. VBE on is 0.7 and beta value is given as 200. Okay, so this is the circuit. Okay, first thing first, you need to identify where is the BE loop and where is the CE loop. Because remember, from the BE loop we can calculate for the currents, from the CE loop we can calculate for the VCE, right? But here in this case, as you can see, at the BE loop, because we have the BE junction here, all right, we have VBB here like this. Okay, so what you can do is complete the circuit, so it will be easy for you to do the KVL equation. So if we complete the circuit, this particular node is actually connected to 4 volt, okay, positive 4, while obviously the negative one is grounded. Okay, so as you know, ground and ground one same level, so from here you can actually see the closed loop and do KVL accordingly. The same thing goes to here, where VCC at this particular node is connected to 10 volt, meaning positive 10. So positive is connected to this particular node, while the negative one is grounded. Okay, so ground and ground same level, so you can see one closed loop here, right? Okay, so the first loop here is actually the BE loop or input loop, and the second loop here is actually the CE loop or output loop. Okay, so from the BE loop just now, actually we can do KVL, where our KVL equation is negative 4 plus IBRB plus VBE equals 0. Okay, and this is the KVL equation. So if we were to rearrange this, we are going to get IB equals 4 minus VBE, which is 0.7, divided by RB, which is 220K. Then we are supposed to get IB 15 micron ampere. This is the same thing. Okay, the same thing like the one that is shown here. Okay, then obviously once we know the value of IB, obviously we can calculate for IC, which is given by beta IB. Okay, substitute accordingly, you are going to get the IC value. Then IE is actually IB plus IC, isn't it? IE is IB plus IC, meaning 3 plus 15 micron, so you are supposed to get 3.02 milliampere. Okay, in this case IB is shown as 1 plus beta IB is actually the same thing, because remember IE equals IB plus IC, then actually IC is beta IB, remember IC is beta IB, so if we factorize we are going to get beta plus 1 IB, which is the same thing like the formula here. Okay, then for VCE, obviously we can consider the second loop, the CE loop. We just do KVL equation. So if you do KVL equation, you are supposed to get minus 10 plus ICRC plus VCE equals 0 for the second loop. Okay, so remember the question is asking for VCE, so we rearrange accordingly. We can get this equation where VCE equals VCC minus ICRC, which is equal to 4 volt. Now let's have a look on example 2. As can be seen from this circuit, we are supposed to calculate for all the currents and the CE voltage. All the resistor values are given, but first thing first, you have to draw the complete circuit. Then only we can see where is the BE loop, where is the CE loop. Okay, so figure B actually shows the actual connections with a complete circuit connection. Then from here we can see the BE loop as well as the CE loop, the input loop and the output loop. Then we consider the KVL equation at the input loop here. Okay, the first loop there. So if we do KVL, we are supposed to get minus 4 plus 0. Minus 4 plus 0.7 plus IERE equals 0 based on this KVL equation in first loop. So from there we can actually substitute accordingly whatever parameters we have. Then we can solve for IE. In this case, IE equals 1 milliampere. Then from there we can actually find for IC, which is given as alpha IE. Alright, then obviously since we know IE equals IB plus IC from KCL, so from there we can actually calculate for IB. Okay, Then we are supposed to calculate for the CE voltage as well. CE voltage normally we get from the CE junction, CE loop. Alright. Then from here we can do KVL equation, normal KVL equation, minus 10 plus ICRC plus VCE, the voltage at between collector and emitter, plus IERE, the voltage drop across the RE, equals 0. So you can get this KVL equation. Obviously rearrange, you can calculate for VCE, voltage at between collector and emitter, which is given by 2.047 volt in this example. Now we come to the second subtopic, which is on BJT load line. In BJT, there are two types of load line, which is the input load line involving IB versus VBE, and there is output load line involving IC versus VCE. Okay, talking about input load line, obviously it is related to BE loop because it is between IB and VBE. It is between IB and VBE. If we talk about input load line, it's actually similar to the diode, because remember at BE junction we have a diode 1PN junction there. So the curve of IB versus VBE is actually just similar to the diode, where we have the curve like this, then the turn on voltage equivalent to 0.7 volt. Okay, the turn on voltage equivalent to 0.7 volt. This is the same curve similar to diode. So in this case, we are supposed to do the load line analysis. So we need to consider the BE loop. So from BE loop, we can do KVL equation, remember? Okay, from here we can do KVL equation. If we do KVL, we are supposed to get this equation. Okay, but now we are looking for the load line equation, meaning we need to rearrange this equation in the form of y equals mx plus c, where y is actually the IB, right? X is the VBE. Okay, so that's why we can rearrange having y, okay, in terms of VBE. Okay, so obviously from here we know what should be the value of M and what should be the value of C. So let's have a look on this particular example on input load line. So from this BJT circuit, we just consider the BE loop because we are considering input load line, right? So for this BE loop, okay, this is the KVL equation. Then we can modify this KVL equation because we want to make it in the form of y equals mx plus c, remember? Okay, so if any question is asking you to provide the load line equation, this is the load line equation. This equation is KVL equation. This is not yet load line equation. The load line equation is the one which is represented with y equals mx plus c. Be careful with that. Okay, so in this particular example, this is the load line equation. So from here, in order for us to draw a straight line on the IV characteristics of BJT, obviously we need to find for at least 2 points. Okay, so for the first point, maybe we can consider if VBE is 0. Okay, if we make VBE 0, obviously in this case IB will be equals to VBB, which is 4 over RB. Right, we can substitute accordingly. Then the second point is we try to make IB equal 0. So at that time, our VBE is actually equals to VBB, which is in this case equals to 4 volt. Okay, so once we have these 2 points, so as you can see from here, when VBE equal to 0, IB is VBB over RB. Okay, we get one value there. Then when IB is 0, VBE equals VBB, which is equals to 4 volt. We get one and another point here. Then we connect them together. Okay, we connect them together. So the intersection between this straight line with the curve, actually will give us the value of Q point. In this case, it should be similar to the one calculated before in BE loop, where IB is 15 micron ampere, then the VBE obviously is at 0.7 volt. Now we come to output load line. So as mentioned just now, output load line is related to IC versus VCE. So as you can recall in previous video, IC versus VCE, okay, for common emitter circuit is represented by this curve. Okay, the higher the IB, the higher value of IC we are going to get. So obviously it is related to CE loop, okay, where we consider the CE loop here, okay, involving CE junction. Then if we do KVL equation, we are going to get this equation, right? VCE equals VCC minus ICRC for this particular circuit. Then obviously to get the load line equation, we need to rearrange it in the form of y equals mx plus c, where y is actually the IC and x is actually the VCE. So from here we can know what is the m as well as what is the c. Okay, for output load line, let's have a look on this example. Obviously now our focus is on the CE loop because we are considering output load line. So if we do KVL here, okay, like previous slide, we are going to get this load line equation. Okay, once we have this load line equation, we need to get the 2 points in order for us to draw a straight line. So first, let's set IC equals 0. In this case, substitute accordingly. When IC 0, our VCE actually equals to 10 volt. Then if we set VCE equals 0, our IC is actually VCC over RC, which is 5 milliampere. Now we have the 2 points. We plot on the graph there, where IC 0, VCE equals 10, okay, this point. When VCE 0, IC equals to 5 milliampere. We have the 2 points, we connect them together. Then we have many curves here representing the IV characteristics of BJT. Which curve we are supposed to choose? You choose the curve which belongs to the correct IB value. In this case, remember previous example, IB we already calculated as 15 micron ampere. So we choose this curve which shows us the intersection between the straight line and the curve, which gives us the value of Q point at IC as well as the VCE. Okay, so this value should be the same that you obtain from calculation. Okay, then only you know your load line analysis is correct. Okay, let's have a look on this example. You are supposed to calculate the characteristics of a circuit containing an emitter resistor. Okay, now you see it's a little bit different compared to previous circuit. And in this case, you are supposed to plot the output load line. Okay, we are supposed to plot the output load line. Calculate the characteristics of the circuits, meaning you are supposed to calculate all the currents as well as the VCE value. In this case, VBE on is given as 0.7, beta is given as 75 no unit. Okay, now since we are focusing on the output load line, obviously we are focusing on the CE loop. Okay, so as you can see from here, remember, draw the complete circuit where VCC can be represented by this. Okay, now you can see one closed loop here, right? We can do KVL equation here. Okay, but first let's have a look on the BE loop. Okay, BE loop, where this is the BE loop involving the VE junction. So as you can see here, it's the RB is connected to 6 volt, meaning the positive 6 is connected to there, the negative one is grounded, ground and ground at the same level. So can you see the complete loop here at BE loop, right? So from here we can do KVL equation. If you do the KVL equation, you are supposed to get -6 plus IBRB plus VBE plus IERE. Okay, so that's why we are getting this KVL equation. Then remember, IE is actually equals to beta plus 1 IB. IE equals to beta plus 1 IB. So in this case, this IE value, okay, because now we are having in this KVL equation, we are having two unknowns, IB and IE. Okay, so in this case, we can replace IE with beta plus 1 IB. Okay, so accordingly, we can solve for this equation where we can find the value of IB in this case is 75.1 micron ampere. Then let's continue with KVL at CE loop. So as we can see here, KVL at CE loop here. Okay, if we do KVL equation, we are supposed to get this equation. Okay, but take note that we are talking about having output load line, which is IC versus VCE. IC versus VCE, right? And in this case, this is our IC, this is our VCE. But take note, IE also you need to substitute accordingly, because IE also can be represented by IC, where IE is actually IC over alpha. Okay, so in this case, you substitute IE with IC over alpha. Okay, then rearrange. In the end, if you plug in all the values given straight away, we are supposed to get this simplified KVL equation. Okay, from there actually you can rearrange accordingly to get the load line equation in the form of y equals mx plus c. So this is the load line equation. Okay, y equals mx plus c. Obviously y is the IC and x is the VCE, right? So from here, the same thing. Once we have the load line equation, you find for the 2 points. First, let's set IC equals 0. Okay, obviously from there you are supposed to get VCE equal to 12 volt. If we set VCE equals 0, we are supposed to get IC equals to 12 over 1.01. Okay, so we can get 11.9 milliampere, the 2 points. Okay, so this is the first point, this is the second point. Once you have the 2 points, connect them together. Then which intersection? We should choose intersection which cross with the curve accordingly related to IB equals 75.1 micron ampere. Okay, so choose this intersection. This should give you the value of IC related to the Q point and the value for of VCE, which is related to the Q point. Okay, but as you can see from here, we are not using graph paper, we are just sketching, right? Meaning to say the value of IC and VCE that we obtain from here is not that accurate. So how can you get the exact value of this ICQ and VCEQ? Actually, you can just calculate. Remember, you already calculated for the value of IB at the first stage. Then obviously we can simply calculate for IC value, where IC equals beta IB. Then IC is given as 5.63 milliampere. Okay, so it should be the same value from the calculated one. And talking about VCE, the same thing. VCE you can actually solve from this KVL equation. Okay. Substitute accordingly, because we already know the value of IC, which is 5.63 milliampere. Substitute there, we are going to get VCE equals 6.31 volt. So the exact value is 6.31 volt, similar to the one calculated. Here is one example that you should take note. Okay, I'm sharing this example because I want to highlight that first thing first, you really need to identify the BE loop and CE loop. Okay, you need to identify the BE loop and CE loop, because for this particular circuit arrangement, this is actually a common base circuit. As in order for you to identify, obviously you need to identify the terminals. Remember, the one with the arrow should always be the E, and here at the base, and here is the collector. So where is the BE loop? easy. The BE loop is the one involving BE junction, right? So this should be the BE loop. But where is the CE loop? CE loop is actually involving CE junction. So this is the C, this is the E, right? So where is the loop? It should be the outer loop here. It should be the outer loop here. Okay, because common mistake that student always did, they see two loops here, they say, oh, this is BE, this is another loop, this is CE loop, which is wrong, because this is the junction between collector and the base, not collector and emitter. Okay, but if you are not sure, you might want to redraw. Where from this circuit, you just redraw into the normal arrangement, where let's say, for example, we have collector, base and emitter. So you check base is actually connected to the ground. Okay, so base is connected to ground and emitter is connected to 10 kilo ohm and eventually to -5. So emitter is connected to 10 kilo ohm, which is the RE here, and -5. Okay, 10k and -5. Negative is already represented with this negative polarity, so the value here is 5 only. Then at the C is connected to 5 kilo ohm, which is this resistor, eventually connected to +15. So +15 VCC is 15 volt. Okay, so if you redraw like this, it will be easy for you to identify where is the BE loop. Obviously this is the loop, right? Okay, then obviously here is the CE loop. Okay, so from there, once you identify the BE loop, you can do KVL equation. Here you can actually get the value of IE, but since beta value is given, you can also find later for the value of IB and also IC if needed. Okay, if you are supposed to find for it. Then coming to CE loop, when you consider CE loop, you can do the same KVL equation. So your KVL equation, double check, VCE plus ICRC, voltage drop across the resistor RC, plus IERE, voltage drop across RE, minus 5 considering the VEE, and minus 15 considering the VCC. Okay, so from here you can actually find for VCE because other values already know. Then in this case, VCE is 13.57 volt. So let's recall, in this particular video, we have two subtopics. The first one is on BJT DC analysis and the second one is on BJT load line. Okay, that's all for this video. Bye.